Hello BC Calculus students, this is Mr. Johnson and this is section 4.5 and we're going to talk about indeterminate forms of different limits and using the L'Hopital's rule to evaluate those. Now L'Hopital's rule is not a new concept to us. So for instance in this class opener we have two different examples of how we've used L'Hopital's in the past. First of all, we have the limit as x goes to 1 of the numerator, which is 0. We also have the limit as x goes to 1 of the denominator, which is 0. And so one of the candidates for one of the limit situations or the candidates for L'Hopital's rule would be when you have 0 divided by 0 for a particular limit. So what you could say here is that we're using L'Hopital's rule. So by L'Hopital's rule, we have the exact same limit as x goes to 1, but this time we're going to take the derivative of the numerator, which is 1 over x, and the derivative of the denominator, which is 1, and we simply plug in the value of x again. We substitute in 1, and we get a value of 1. So this limit happens to be 1. Prior to doing L'Hopital's rule, we have 0 over 0, which means that we cannot determine what's happening. That's an indeterminate form. And again, this is one that we used last year. With the second example, we have the limit as x goes to infinity of the numerator, which is infinity. And then we also have the limit as x goes to infinity of the denominator, which happens to be infinity. So in this case, we have infinity divided by infinity, which is another indeterminate form for limits that we had last year. So in this case, we do the same thing. We have L'Hopital's rule, and we have our limit as x goes to infinity, and we take the derivative of the numerator, derivative of the denominator, and we have 1 divided by infinity, which is equal to 0. So again, we have two situations, both of which we had talked about last year. We've done examples last year. We've used L'Hopital's before. We've been tested on it. What we're going to do now in the rest of this section here, the remaining examples that I'm going to work through with you, is we're going to talk about much more complex indeterminate forms that we're going to start to see a little bit more in this class and then beyond. The rest of this page is going to be just an overview of L'Hopital's rule and when we can use it. Keep in mind that the two conditions for which we can use L'Hopital's rule are going to be when you have 0 divided by 0, or infinity divided by infinity, or the negative version of infinity divided by infinity. So what we're trying to do with every problem I'm about to show you is we're trying to get it to be one of these two forms, 0 over 0 or infinity over infinity. Keep in mind that the positive and negative infinity over infinity doesn't matter. We're trying to force every problem into that format so that we can use L'Hopital's rule. So let's go ahead and begin on the next page. All right, at the top, you can see that there are 7 different indeterminate forms, and the first two were the ones that I just discussed, and those two are from AB calculus. The remaining ones are really what we're going to start to dig into here in BC calculus. So we have infinity minus infinity, which I know you all are thinking that's going to be 0. It very well may be, or it could be really anything else. Remember, infinity is not a number, so we can't treat it as we would normally with numeric operations. So if we have 2 minus 2, we know that's 0. But infinity minus infinity doesn't follow the same principles because it's a description of a behavior. It is not a number itself. Same thing here. We have 0 times infinity. Well, 0 times another number is 0. The problem is infinity is not a number, so 0 times infinity is indeterminate. 1 to the power of infinity, of course 1 to any power of a number is 1. However, infinity is not a number, so you get the idea here. All of these are indeterminate. 0 to the power of 0 is a strange one. I'll show you an example of that. It obviously doesn't have infinity in there, but it is in the indeterminate form. All right, the first one we're going to look at is infinity times 0. So you can kind of read through this description, but basically if you have a situation where you have 0 times infinity, that obviously fits into one of our 7, and we want to force it into a fraction so that we can really get into a situation where we can use L'Hopital's rule. So we want to go from something that is 0 times infinity and turn it into either 0 divided by 0 or infinity divided by infinity. And so let's just double check that this is in fact 0 times infinity. We're evaluating the limit as x goes to 0 from the right, and we have 0 and then natural log of x. Now remember, the natural log of x as we approach 0 from the right will be actually negative infinity, because we're going to approach from the right side of 0. We're going to go and approach negative infinity. So in other words, this particular one is 0 times negative infinity, which is this indeterminate form that we're going to discuss at the beginning here. So what we're trying to do is set it up as a fraction. Now you could set it up as the limit as x goes to 0 from the right side of ln of x divided by 1 over x. That's totally fine, because that is the equivalent of the original, but now it's in a fractional form. You could also set it up as the limit as x goes to 0 from the right of x divided by 1 divided by ln of x, and that would also be the equivalent. Now you're going to find that depending on the strategy you use, one is going to be much better than the other. And so you can probably just see visually that this green one is going to be a little bit more difficult. And so we are going to go with the one on the left here. We're going to do the limit as x goes to 0 from the right of the natural log of x, which we know is negative infinity. And we're going to look at the limit as x goes to 0 from the right of 1 over x, which happens to be positive infinity. So what we get here is negative infinity divided by positive infinity, which is in the form we need for L'Hopital's rule. Okay, so we have L'Hopital's rule. We're going to take the same limit as x goes to 0 from the right side. We have the derivative of the natural log of x, which is 1 over x. We have the derivative of 1 over x. Remember, 1 over x is really just x to the negative first. So we have negative 1 over x squared. And I'm putting a lot of parentheses in here, I suppose. So that's our format here. If you were to try the limit right now, you're going to come across some issues because of all these fractions. So what I suggest is to simplify before you actually try your limiting value. We have 1 divided by x divided by the quantity negative 1 over x squared. If we think about this, this is the same thing as 1 over x times negative x squared over 1, and that is going to be the limit as x goes to 0 from the right of simply just negative x, which of course is 0. So not too satisfying here. We started with this 0 times negative infinity, and naturally we think to ourselves, well, that's got to be 0, right? And no, sometimes it's not, but in this case, it does happen to be 0, which I know is not satisfying. Hopefully with some of the other examples I'll show you, you'll be satisfied that the answer is not always what it seems. Okay, let's move on to the next page. All right, on this page, we're going to look at another indeterminate form. This one is infinity minus infinity. And again, I discussed this just a second ago, a couple pages ago, where our natural response to this is that infinity minus infinity must be 0. But remember, infinity doesn't follow the same principles or properties as any kind of real number. And so in this case, we don't know. We are trying to get it into the 0 divided by 0 or infinity divided by infinity form. And this is going to be a bit algebraically challenging, I think, for some people. But let's go ahead and work through this. First of all, does this actually fit our particular form? Well, when we first look at e to the power of negative x, if x goes to infinity, e to the negative infinity is 0. E to the x then, if x goes to infinity, is infinity. So we end up getting infinity for that first ugly phrase there. And then in the second part, e to the x would obviously be infinity as well. And so we end up getting infinity minus infinity. All right, let's work to get this either into 0 over 0 form or infinity over infinity form. And the goal here is to algebraically manipulate it as best we can. The first thing I'm going to do is I'm going to separate this first phrase and break up the power. So I'm going to take, we clearly have limit as x goes to infinity, but I'm going to take e to the x and multiply by e to the negative x. So we're splitting that up. We still have minus e to the x. The reason I'm doing this is because now I can factor out an e to the x. So we have e to the x multiplied by e to the power of e to the power of negative x minus 1. Okay, we're still not in 0 divided by 0 or infinity divided by infinity, so we're going to want to manipulate this again. We have the limit as x goes to infinity of e to the power of e to the power of negative x minus 1 divided by e to the negative x. So I'm moving this portion of it right here, e to the x. I'm just writing it as e to the negative x in the denominator. Remember, all of these three are equal. I'm just making algebraic manipulation steps because now all of a sudden we have a fraction, which again we're looking for some sort of fraction. And excuse me, not only that, but we have the limit as x goes to infinity of the numerator, which is e to the negative x minus 1. So remember, e to the negative x, if x goes to infinity, is 0. E to the 0 is 1 minus 1 is 0. So I have 0 in the numerator. I have the limit as x goes to infinity of the denominator, e to the negative x. That is 0. And so we get 0 divided by 0. Keep in mind, this whole time I have never written equals 0 over 0 or equals infinity over infinity. That would be something that AP does not want to see. So we have a situation where L'Hopital's rule does apply. Okay, I'm going to take the derivative of the original numerator. Now keep in mind that with e to the negative x, I am going to get that in return when I take my derivative. That's one of those properties of e to the x. So I'm going to get that, but I have to multiply, because of the chain rule, by the derivative of e to the negative x. So the derivative of the numerator, I know it's kind of messy, but I'm just trying to walk you through it, is negative e to the negative x. That part is the derivative of this exponent right here, okay, because of the chain rule, times e to the negative x, which is that original, because remember the derivative of e to the power of a function is e to that power of a function. The derivative of 1 is of course 0. In the denominator, I have the derivative of e to the negative x, which is kind of nice algebraically, because guess what we can do? We can cancel this. Let me change colors. So we can cancel these two, and we are left with, and remember what I said, you must try to cancel before you try to substitute again, just because if you substitute too early without canceling, it's going to possibly cause an error or maybe more work for you. Okay, remember e to the negative x, if x goes to infinity, is 0, so e to the 0 is 1. So amazingly, infinity minus infinity in this example is 1, which means that, again, we can't assume that it would just cancel and be 0. All right, let's go ahead and try the next one. So here we have the same type of situation. I'm showing you a second one of these. So the limit as x goes to 1 from the right of the first part, so 1 divided by x minus 1 would be infinity. And remember, I showed you the graph of the natural log of x. So as natural log of x approaches x is 1 from the right, we get really close to 0, and it's positive. So 1 divided by a very small positive number is going to be infinity. And so this is indeterminate. We need to try to wiggle this one around a little bit. One of the best things we can do with separated fractions is to combine them algebraically. So if we have the limit as x goes to 1 from the right, I'm going to just create a common denominator through multiplication. So I'm going to multiply the fraction on the left by the natural log of x divided by the natural log of x, and I'll do the same strategy except the other denominator. So I'm creating a common denominator so that ultimately we can add these up. So I have the natural log of x minus x plus 1 in the numerator, and then in the denominator we have this product. Okay. The question is, did we successfully set up a 0 divided by 0 or an infinity divided by infinity situation? So let's take a look at the limit as x goes to 1 from the right of the numerator. And again, ln of x as x goes to 1 from the right is 0 minus 1 plus 1, and so we get 0. That's so far so good. Then we have the denominator, and again we have 0 for x minus 1, and then ln of x as x goes to 1 from the right is 0. So we get 0 times 0, which is 0. Okay, so we're going to use L'Hopital's rule. Again, we have the condition that we want. Okay. All right, we have the limit as x goes to 1 from the right, and we're going to take our derivatives. So the derivative of the natural log, which is 1 over x, minus 1, divided by, we're going to get a product rule here, so it's going to be a little bit ugly. The derivative of x minus 1 is 1 times ln of x, plus x minus 1 times 1 over x. Now we do have a complex fraction here because we have multiple fractions within one fraction. So one of the easiest ways to simplify this is to multiply both the numerator and denominator by x divided by x. And what that's going to do is it's going to clear these fractions that are within the fraction. It's just going to simplify it a little bit. This doesn't necessarily mean that it's going to absolutely help us come up with a limit right away, but what it does help us do is to simplify it down so that we can, at least figure out, are we going to have to do L'Hopital's again, or are we going to be able to actually get down to an answer? So what we get here, and again, what I'm doing is I'm taking x and I'm multiplying it through to the different terms in the numerator and denominator. So for instance, when I multiply it through to the 1 over x, x times 1 over x is just 1, minus 1 times x is x. So we have 1 minus x in the numerator. In the denominator, I have x times natural log of x. Again, I'm distributing this through like this, okay? Now keep in mind, this is a product. So I have x times 1 over x, which cancels to 1. So I'm going to get x times ln of x plus x minus 1 in the denominator. All right, the problem is right now that I really can't do much more with this in terms of simplification. So let's take a look at what's happening. We have the limit as x goes to 1 from the right of the numerator, 1 minus x, that's 0. I have the limit as x goes to 1 from the right of the denominator, and that happens to be 0 as well. And so unfortunately, we have to do L'Hopital's one more time. Okay, so we have the limit as x goes to 1 from the right. Now I'm up here in the original. I need to take the derivative of the numerator, which is negative 1. I need to take the derivative of the denominator, which means I need to use the product rule. So x times ln of x would be ln of x plus x times 1 over x. And then we have the derivative of just x, which is 1. And then, of course, the derivative of negative 1 is 0. And so we have this. Now, I'm going to simplify this one step. I promise we are almost done with this problem. So we have negative 1 in the numerator. We have the natural log of x, and x times 1 over x is just 1. And I'm going to add that to this one. So I'm going to get plus 2 here. Okay, the natural log of x at 1 is 0, and so we finally have our final answer, which is negative 1/2. Okay, let's move on to the next page and talk about another indeterminate form. All right, this is the last set that we're going to talk about, and this is going to be 3 different types, the 0 to the 0 power, infinity to the 0 power, and 1 to the infinity power, and it kind of rounds off the remaining of these 7 indeterminate forms. You can look through the notes. It kind of goes through the same thing. Our entire goal here is that we want to set up a situation where we're able to use L'Hopital's rule. So we want to get it to a spot where we're able to do 0 over 0 or infinity over infinity. All three of these typically take the form of what is described here in the middle, which is to use the natural logarithm, which you have seen, but it's been very brief. This form is also a possibility, but I think that this natural log form is probably the easiest one with any of these three types of indeterminate forms. So let's take a look at the first one. Now with the first one, we have 1 plus sine of 4x. So if x is 0, sine is 0. So we have 1 cotangent. So think through cotangent. Cotangent is 1 over tangent, and tangent of 0 is 0. And so if we're approaching the tangent function from the right side of 0, which means with cotangent, we're approaching from the right side, we're actually approaching positive infinity there, okay? Because what we're doing is we're taking 1 divided by a very small positive number. So in this problem, we are getting the indeterminate form of 1 to the power of infinity. And again, the whole approach is the same as what we've done so far, which is to make sure that we set up a condition for L'Hopital's rule to be applied. So in this one, let's start with writing as y equals 1 plus sine of 4x all to the power of cotangent of x. You can use anything you want other than y. It doesn't really matter. Just don't use x because it's already assigned. I'm just using y because it's a little bit more natural, but it's just a dummy variable. We're going to deal with it later. The next thing we're going to do is take the natural log of both sides. On the last two examples, I will not do this additional step, but for right now, I want you to see what's happening. So remember, with the natural logarithm, we're able to take the power of the argument, which is cotangent of x, and bring it to the front of the logarithm. This is just a property of logarithms. So we're left with this. That was sort of the key to using the natural logarithm, because you want to make sure that you can access the exponent, which in this case was cotangent of x. Okay, the next step is that we're going to take the limit of both sides. So we have the limit as x goes to 0 from the right of the natural log of y, and the limit as x goes to 0 from the right of cotangent of x times natural log of 1 plus sine of 4x. Okay, if we focus on the left side first, remember your limit is going to be first done by substitution. So the first thing we would do here is plug in 0 for x. Well, there is no variable of 0, which means that this particular limit is simply just the natural log of y. So on the left side, nothing much changes. We'll deal with that later. We'll just keep it here. Now on the right side, we have an issue because we have a product. So we have cotangent of x. Now remember, we already talked about this. This is infinity. And then we have the natural log of 1 plus 0 if x goes to 0. And so we have the natural log of 1, which is 0. So, and I'll just write this off to the side. So we have infinity times 0. Now that's an indeterminate form. We already knew that we had to put this into some sort of fractional form in order to use L'Hopital's rule, but this just confirms that we still are in trouble as it's written right here. We need to make this a fraction. Now the easiest way to do that would be to use cotangent and turn it into just division by tangent. So in other words, we're going to kind of keep that trig identity here. So we have the limit as x goes to 0 from the right of the natural log of 1 plus sine of 4x divided by, and I'm just going to make it tangent because instead of multiplication by cotangent, division by tangent is the same thing. Okay, let's double check that we're in a situation where we can apply L'Hopital's rule. So the limit as x goes to 0 of the natural log of 1 plus sine of 4x. We know that's 0. We have the limit as x goes to 0 of tangent of x, and we know that's 0. So we get 0 divided by 0. We're happy. This is a situation where we can apply L'Hopital's rule. So our first step, and again, remember we have the natural log of y. So our first step is to keep the limit the same. So we have x goes to 0 from the right, and we have 1 divided by 1 plus sine of 4x. However, we have to multiply by 4 times cosine of 4x because of the chain rule twice, basically, right there. So that's our numerator. And then we have to divide it by the derivative of tangent, which is secant squared of x. Okay, that looks really ugly, but let's go ahead and try substitution. So we have sine of 4 times 0, which is 0. So that's just going to be 1. Let me go ahead and write out natural log y. So we have 1 there times, and then this is 4 times cosine of 0. Cosine of 0 is 1. So we have 4 times 1, which is 4. And then we have secant squared. Remember, secant is 1 over cosine. Since cosine of 0 is 1, that's 1. And so we have the natural log of y equal to 4. And remember, we're trying to solve for y because at the very beginning we set it up as y equals. And if we just use properties of logarithms and exponents, we have y equal to e to the 4th power. And believe it or not, that is your limit. Okay, I have 2 more for you. Let's go on to the next page. Okay, here's your first one. Some of you that have studied the number e know that this answer is e. If you don't, that's okay, but you should know this limit. This is a very common limit, and it's a limit that is utilized more and more in higher levels of math. This is one definition. This is one limit definition of e, and I'll go ahead and show you by using the indeterminate forms that we've talked about. So if we have n going to infinity, 1 divided by infinity is 0. So you have 1 to the power of infinity, and that's one of our indeterminate forms. Okay. Again, our answer is going to be e, so we're going to get e out of this. All right, let's go ahead and set up our y equals 1 plus 1 over n to the power of n. We're going to take the natural log of both sides. I'm going to save a step here and apply that property of logarithms that we did in the last problem just to save ourselves a step. Then we're going to take the limit as n goes to infinity of the natural log of y, and the limit as n goes to infinity of n times natural log of 1 plus 1 over n. We know that this portion must be in some sort of fractional form to apply L'Hopital's rule. We know this side is just natural log of y. So here what we're going to do is move the n because it's much easier to move that than it would be anything else. So we have the limit as n goes to infinity of the natural log of 1 plus 1 over n divided by 1 over n. So that's how we're going to move it algebraically. Now if we just double check that we're all set up here, we have the limit as n goes to infinity of the natural log of 1 plus 1 over n. That is 0 because we end up getting natural log of 1. Then we have the natural log as n goes to infinity of 1 over n, and that is of course 0. Oh, I don't know if I said this wrong or just wrote it wrong. Correct this. The value here should be infinity. Okay, so limit as n goes to infinity of 1 over n is 0. So we have 0 divided by 0, which is exactly what we want for L'Hopital's rule. Now we have the limit as, we have the natural log of y equal to the limit as n goes to infinity, and we're going to take our derivatives. So in the numerator, we have 1 divided by 1 plus 1 over n times, remember we're going to do the derivative of 1 over n because of the chain rule. And that derivative is negative 1 over n squared. In the denominator, we have really the same thing there, negative 1 over n squared. And similar to one of the other problems that we had, where we were dealing with this type of situation, we can cancel these two. And so what we're left with is the natural log of y equal to the limit as n goes to infinity of 1 over 1 plus 1 over n. And remember, if we have 1 over infinity, it's 0. So this really is all going to simplify to 1. And don't forget, that's not your final answer. You're going to get the natural log of y equal to 1, which means that y is equal to, and there's our answer, it's e, just like I advertised at the beginning. Okay, one last one. We have x to the power of x. So we have y equal to x to the power of x which gives us the natural log. I'm going to save us a step again. We have x times the natural log of x, and we're going to take the limit of each of these as x goes to 0 from the right side. Now, if you remember, we ended up doing this exact problem in example 1. In example 1, we got 0 out of that. And remember, on the left side, this is going to simply be the natural log of y. So what we get here is the natural log of y equal to 0, which means that y is equal to e to the 0, which is going to be 1. Okay, on the next page of your notes, you have some examples to try. I do promise you that they're much easier than the set that I just went through, and you're utilizing L'Hopital's, you're just reviewing L'Hopital's concept. And in the notes here, we have the answers for those problems to practice. But that does it for section 4.5. Thank you.